Good morning and welcome back to the new session. In the previous class, we were discussing about the RC model of NAND gate, 4-input NAND gate. And we got to know that if we have more number of inputs, in that case, not only the delay component is a function of load capacitance, but it is also the function of internal capacitances associated with all the transistors. Okay, and this is really very important that need to be considered. So one very important thing, thing that need to be considered here is like if I have more number of transistors. So here, if you see here, if I have more number of transistors, we will have more internal capacitances, and the total the total time taken by this circuit to discharge the capacitor or load capacitor, that is a function of all the capacitances. Like suppose I have this CL, so this CL will become the function of how to discharge this CL. This will be CL, R4, R3, R2, and R1. So this will be the discharging time constant for this CL. Similarly, because we have other capacitors as well over here, so this capacitor will also take some time to discharge. So the total TPHL component will be increased by these factors. So here, if I have to discharge this C3, so that will the total discharging time constant will be like C3 into R3 plus R2 plus R1. Similarly, for C2, it will be R2 plus R1, and for C1, it will be C1 into R1. So the total discharging time constant will be something like this. And this is one of the problem. Why it is like if I keep on increasing the number of transistors in stacking, the total time component or like these components will be increased by some factor. Okay, and that results in the more delay. Okay, so the propagation delay will be increased. So to overcome that problems, what are the solutions? We need to know what are the alternative solutions. So I will explain all those solutions. How we can remove these problems. But before explaining the solution of these problems, whatever I'm saying, like see, if I can see here, if I have to discharge this output load capacitances, so I need to discharge these capacitances as well. Okay, and these all are the function of these things. So this will overall increase the delay. Okay, so how to optimize that, I will tell you. As I can, we know that if I'm talking about the NAND gate, okay, so in NAND gate, we know that if I have two input NAND gates, so two PMOS transistors will be in the parallel in the pull-up network, and two NMOS transistors will be in the series in the pull-down network. Similarly, if I have three input NAND gate, in that case, three PMOS transistors will be in the parallel, and three NMOS transistors will be in the series in the pull down network. So what it means? It means that if I keep on increasing the number of inputs in a NAND gate, in that case, there is no component in the series in the pull-up network. All the components are, all the transistors are in the parallel. So the total time constant or the worst case time constant will be like is equivalent to the single transistor activation. Let me repeat it again. What I'm saying. Suppose even though I have, let us assume n number of inputs in the NAND gate. So what will happen? There will be n number of transistors which will be in the series in the parallel. Okay, and the worst case delay component for TPHL from high to low. Low to high, because I'm charging through pull-up network. So from high to low, time constant will be the worst case if any one of the transistor is activated. So and other thing like the time constant will be reduced if I am keep on increasing the transistors in parallel. So the worst case always be equivalent to one transistor. Okay, but if I'm talking about this pull down side, which is the TPHL, high to low, if I'm keep on increasing the number of transistors in the series, the TPHL will keep on increasing. Now means what it means? The TPLH, the worst case TPLH was a function of a single transistor activation, but the worst case TP HL is the function of the activation of all the transistors which are in the series. So if I'm increasing the number of inputs in the NAND gate, the delay will further increase. Okay, and the number of input is nothing but this, we call it the Fanin of the circuit. So Fanin is nothing but how many inputs we can connect in a circuit, that we call it the Fanin. So if I'm increasing the Fanin of any circuit, the TPHL will increase, but TPLH will be almost same, or the worst case TPHL will be LH will be same. Yes, any question? Okay, so this is how we can define. Similarly, if we talk about the NOR gate, okay, in NOR structure, what is the things? The thing is like the pull-up network is in the series and the pull-down network in the parallel. So if I have the NOR gate, in that case, the TPLH will be the function of fan-in, whereas the TPHL will be the equivalent to the single transistor activation. So this is the difference between these two things. So let us try to summarize it. The propagation delay as a function of fan-in. Suppose I have a NAND gate, okay, and if I have a NAND gate, and let us try to check the fan-ins. Like suppose initially the fan-in in 2, then fan-in in 3, then 4, 5, and 6, something, and so on, whatever it is. Okay. So can anyone tell me how the TPHL and TPLH will vary with respect to the fan-in? I just discussed this thing.
TPLH will remain constant as fan-in.
Okay. So TPLH will be remain constant in case of NAND gate, and TPHL will be
increased with fan-in.
That will be increased with respect to the fan-in. Okay. So if I can draw a simple curve, so like let us assume this is the TPLH, and if we talk about the TPHL, so TPHL will be something like this one. Okay, so TPHL will look like this one for NAND gate. Similarly, if we talk about the NOR gate, so like it will be opposite to this one, right? So we just understand how it will be. So the so this will be, yeah, let me change the color so that will be better. Okay, so let me make this one. So this is the TPLH, and this is how TPHL will look like. So this is the characteristics of both the delay component, and that is the function of the fan-in. Okay, and we need to optimize. So the important thing is, if I'm talking about the NAND gate, in that case I need to optimize the pull down network if I have to make the less propagation delay. So we have to do some exercise on the pull down network so that we can have the less delay. Similarly, if I'm designing the NOR gate, in that case I need to do some exercise, some modification on the pull-up network side so that we can reduce the TPHL so that we can get the less propagation delay. So this is the important point of consideration, like which of the section in a pull-up network, like in a NAND gate or in the NOR gate, I have to consider for delay optimization. Okay, so in the NOR structure, I have to consider the pull-up network to be optimized, and in NAND structure, I have to consider pull-down network to be optimized. Okay, so this is the important thing. Now the question is how to optimize the propagation delay if I have this kind of the things, like this kind of behavior we are getting. So how to optimize the delay? So in the next slide, so design techniques for the large fan-in. So if I have the large fan-in, in that case, what are the solution to reduce the delay? So the first solution is the transistor sizing. What is that? I will tell you. Second solution could be the progressive transistor sizing. Third solution could be the input reordering. And the fourth one could be logic restructuring. Okay. So let us discuss one by one. What is the transistor sizing? Before I explain the transistor sizing, let me go back to some previous concept which we have already studied. We know that if I am increasing the size of any transistor, like if I am increasing the width of any transistor, the equivalent resistance or the on resistance will reduce. Okay, so suppose I have to reduce the delay. In that case, what I can do, I can simply increase the size. Okay, so let us discuss these things. So let me write a few things here. Okay, so the propagation delay will be reduced if I will increase the size of the transistor. Okay, but if I will increase the width of transistors, the propagation delay will be reduced. Let me write in opposite way. Okay, so if I'm increasing the width, then TP will be reduced. But the problem is, if I will increase the width of size, like see, the first solution could be like just increase the size of transistors and you will get the less resistance, on resistance. And if we have the less on resistance, the delay will be reduced. So this is the simple concept, straightforward concept which we can interpret. But the problem is, if I will increase the width of any transistor, definitely it will reduce the resistance, on resistance, but the parasitic capacitances associated with the transistor, that will increase. Okay, so if the parasitic capacitances are increasing, so we will not get that much. Like, so say, even though I'm trying to reduce the propagation delay by increasing the width, but the additional parasitic capacitances, like the increased in the parasitic capacitances, that will further lead to increase the propagation delay. Okay, so this will not reduce the delay, but it will maintain the same delay even though I have increased the width of the transistors. And this concept is known as self-loading effect. This effect is known as self-loading effect. Let me repeat it again. What is the self-loading effect? Suppose I have to reduce the propagation delay. For that purpose, what I can do, I can simply increase the size of the transistor. Okay, so suppose I am increasing the size of transistor, and that will effectively reduce the on resistance. Okay, so R on will be reduced and propagation delay will be reduced. So this is the thing which we can simply say. But because I am increasing the width, that increase in the width will lead to increase in the parasitic capacitances. So let me write it perfectly. C parasitic. Okay, C parasitic will also increase. And if C parasitic will also increase, what it will include? It will increase the propagation delay. And if it will increase the propagation delay, like the delay will be matched. And even though I have increased the size of transistor to reduce the delay, there will be self-loading, like this parasitic capacitances will try to increase the delay. And this effect is known as the self-loading. Okay, and the propagation delay will be unaffected. Okay, so this is really very important to understand. Like we need to be very careful, especially if I am trying to reduce the propagation delay by increasing the width. No, it is not that much simple. Theoretically, it looks like very simple, like just increase the width and reduce the resistance, and then you can reduce the propagation delay. But practically, some other side, like the secondary effects comes into the picture, and those secondary effects are the parasitic capacitances. So these kind of effects will lead to the propagation delay will be unaffected. And if it is unaffected, unnecessarily we have increased the area by increasing the W, but we are not getting any benefit in terms of the delay. Okay, so this is really one of the challenge, especially if I'm trying to reduce the propagation delay by increasing simply the size. Okay, so to overcome this problem, what we can do, let us try to see. Okay, second solution could be the progressive transistor sizing. Okay, before explaining these things, let me go back to the previous slide which I just explained a few minutes back. Here if you see here in this particular slide, what we understand that this TPHL is the function of the time constant for this C1, time constant for, like time taken to discharge the C2, time taken to discharge the C3 and the CL. Okay, and if you see closely, this R1s appears 4 times. Let me use the highlight pointer. If you see here, R1 was the part in C1 discharging, R1 was also the part in the C2 discharging, R1 was in the part to discharge C3, and similarly to discharge C4. Okay, so this R1 is the important component here. If you see in this particular circuit, like if I have a NAND kind of a structure, and in NAND structure, this R1 becomes one of the important component in the TPHL, and this involved in all the discharging component. Either I have to discharge the C1, C1, C2, C3 or CL, R1 is always present. Okay, if I have to reduce this TPHL, what could be done? If somehow I can reduce this R1, then effectively we can reduce more precisely. We can reduce this TPHL more precisely, because this R1 will reflect in all 4 components. Okay, here, all the 4 components, like this R1 will be affected. So the overall TPHL we can improve in the better way. So the important thing is, like, if somehow I can reduce this R1 instead of reducing all the resistances, so I will get like better performances like TPHL, lower TPHL. Okay, and so this is all about the R1. Similarly, if you see R2, so R2 is responsible in 2 components. Here is R2, here is R2, and here is R2. Okay, so R2 has 3 components, R1 has 4 component, R3 has 2 component, and R4 has 1 component. So if I can reduce this R1 with more values, like if I can keep the size of this transistor M1 maximum, and then somewhat lower size for M2, then somewhat lower size for M3, then somewhat lower size for M4, like if we can, like progressive sizing we can do, in that case these components will be reduced. Is there any doubt what I'm saying? This is really very important to understand the transistor sizing. Okay, and how we can do that. So let me repeat it again, what I'm saying. If I have this much of NAND structure, in that NAND structure, this R1 is the part of 4 components. Okay, so if somehow I can increase this size of this M1, so that will lead to reduce this TPHL. Okay, because this R1 is having 4 component, and that we can reduce this one. But if somehow I can increase all the transistor with the same amount, so again the same problem will come, like what I just discussed a few minutes before, like the self-loading effect. So to overcome that self-loading effect, we can increase, or we can set the transistor sizing in such a way that which transistor is involved how many times. Like this M1 is responsible for these 4 components, and similarly M2 is responsible for 3, and M3 is responsible, something like that. So progressively we can assign the sizing so that we will get the better delay component. Okay, so let us try to explain that one. Okay, so here I have all these things, like let us assume I have the n input sizing. In that case, what I can do, the simple solution could be, what could be the simple solution? Simply what I need to do, the transistor of the sizing of M1 should be maximum, then M2, then M3, then Mn. So the transistor which is close to output voltage must have the minimum sized. Okay, and the transistor which is close to the ground must have the maximum size, so that we can reduce the delay. Okay, so this is the second solution to reduce the delay. Third solution could be like input reordering. Okay, what is that input reordering? Input reordering means, suppose I have this kind of the pull down structure, like I'm talking about the NAND gate. Okay, so if I have the NAND gate and I have this kind of structure where I have this input 1, input 2, and input 3. Let us assume input 1 and input 2, these are already kept to 1. Okay, so let us assume I1 IN3 is equal to 1 and IN2 is equal to 1. What it means, this transistor M3 and transistor M2 is in on state. Now whatever the output we are assuming at this point, this output now depends on the switching activation of this transistor, this input I1. Okay, let me repeat it again. Let us assume I have 3 transistors in the pull down network, like I have the 3 input NAND gate. Okay, so this is, I have just made the structure of the pull down only. I'm not considering the pull up, because in the pull up network we have all the transistors in the parallel, so the effective time constant will be or the worst case time constant will be the single transistor only. So we don't need to take care of that thing. Yeah, but if I'm considering the NOR gate, in that case I need to do the same exercise but in opposite way. So if I'm considering 3 input NAND gate and I have drawn this pull down network of 3 input NAND gate, so I have 3 inputs, IN1, IN2, and IN3. Let us consider IN2 and IN3 are kept at logic high. What it means, M2 and M3 are in on state. Okay, these 2 transistors are in on state. Now the whole responsibility goes to IN1 to change the logic at output voltage. If this IN1 is 0, in that case this output will not be reflected, even though we have turned on these 2 transistors M2 and M3. But if this IN1 becomes 1, in that case all these transistors will be in on state. Now this output will become low, because all the transistors in series will be in the on state. Okay, so the important thing is, even though because see, I just told you internal capacitances have, yeah, I think there is some, this is not the line here, it should be inverter. Yeah, so let me make it perfect. Okay, so suppose I have all these capacitors. Okay, so if, let us assume, if IN1 is equal to 0, if I1n is equal to 0, so this CL will be not discharged, this C2 will not discharge, and this C1 will not discharge, because all the internal nodes will have some capacitances. So this C1, C2, and CL, C2, and C1, these all will not discharge. Once this input will change its logic from 0 to 1, then this part, this capacitor C1 will discharge through M1, this C2 will discharge through M1 and M2, and then this CL will discharge through M3 and M1, M3, M2, and M1. Okay, so the important thing is, like, if the function, like whatever the circuit I have, if this is the function of input 1, in this case I need to discharge all these capacitances to make this output low. Okay, and that will take more time. Now let us consider the another one. I know that if I know that this input one is the important input which decides the function. Okay, so let us consider the same, like I13 is 1, I2 IN2 is 1. So if this is 1, so this M3 will be in on state, so this capacitor will be discharged. This capacitor is already discharged because these two transistors are in on state. Now if the input is changing from low to high, so what I need to do, I need to simply discharge this load capacitance only, not these two capacitance, because these two capacitances are already discharged because IN3 and IN2 are logic 1. And if IN2 and 3 are logic 1, in that case, I don't need to discharge C2 and C3 capacitors. I just need to discharge the CL. So the total time taken to discharge this load capacitance will be less as compared to the previous case. And if it is like that, what it means? It means that you can reduce the delay. So you don't need to do anything. You don't need to change the sizing, but simply by reordering the inputs, you can reduce the delay. So what you have to do, you have to simply find which of the input is the critical input. Okay, critical input means which decides the logic, which decides the function. Okay, so if you know the critical input, in that case, you can keep that critical input very close to the output node, so that you will have the lower delay. Is there any question? This is really very important. Plus, please take 1 minute time and try to understand what I'm saying.
Sir, we are assuming here that before that input 1 goes from 0 to 1, that the C2 and C3 have discharged.
Yes, why they will discharge? See, because if you see the case 1, in the case 1, even though M3 and M2 are in on state, but there is no path because M1 is off. If M1 is off, like, so I'm assuming that IN1 is 0 and all other inputs are 1. So even though M2 and M3 are in on state, there is no path to discharge C2 and the C1. There is no path to discharge this one. Okay, so if there is no path to discharge, so once this I1 will be high, then all the capacitor will be discharged in the first case. But if you see the second case, because IN3 is 1, IN2 is 1, so if this is 1, this C3 will be discharged through this M1 because this is on. Similarly, this C2 will be discharged through this M2 and M3 because both the transistors are in on state. So once this input is changing from 1 to low, like I1 in changing from 0 to 1, in that case I have to discharge only this CL, not C2 and C3, because this C2 and C3 are already discharged well before the transition. Okay, so if they are discharged, so it will take less time. You got the answer?
Yes, sir.
Okay, so this is how the input reordering is really very important to understand the to reduce the delay in one. Okay, so I just mentioned one important term, which is the critical node or the critical input. So the critical input is the input which decides the function or the logic change in a particular circuit. Like in this case, if you see IN2 and 3, these two are not the critical input, but IN1 is the critical input because the change is in this input is deciding the output. Okay, similarly in the second case also, this IN1 is the critical input. Okay, so these are the critical input, and the path which is taken from the critical input to the actual output, like this is the critical path. Okay, so this one, like C1, C2, C3, this is the critical path in this case. And if we talk about the critical path in this case, I have only the critical path which is only M1. Okay, in the first case, the critical path will be through M1, M2, M3, And in the second case, the critical path will be only M1. So we will have the reduced critical path. And if we have the reduced critical path, the delay will be reduced. So the important thing is somehow you need to reduce the critical path in a circuit. Okay, so this is really important, and that you need to understand the things. Okay, so this was the another question. Now the second thing is this was the input reordering. Is there any question? Anyone? Any doubt? You can ask, because this is really very important to understand the concept, like how we can optimize the things.
So this, like, I'm understanding that M2, M3 is already discharged, but this blue discharge path that you have drawn, that I'm not getting.
Blue discharge path? No, blue is not a discharge path. It is the critical path. Like what? Let me tell you this, because see, in the first case, in the first case, I have provided IN1, IN3 and IN2 at logic 1. Okay, and this IN1, the change in IN1 decides the change at the output. Okay, so if any input which is deciding the function of output, okay, output, so that node is known as the critical node, okay, or the critical input, and the path between critical node and the output, that we call the critical path. So here in this case, in the first case, the critical path is in between M1, M2 and M3, because the IN1 is the critical node, critical input. And in the second case, IN1 is the critical input, but this is very close to output. So this is the critical path between the M1 and the output only. Okay, so critical path is not just like the gate one. This is the in between input, which is the critical input, and the output.
Okay, sir. So we can say that if that it is shorter, the
Yes,
critical
yes,
path
yes,
is
yes.
shorter, then
It is the shortest path between the output and input. Okay.
So the shorter the critical path is, the better it is.
Better, yes, perfect. So the shorter means it will have less capacitances, and if we have the less internal capacitances, like the propagation delay will be less. So the ideally the critical path should be shorter, or it should be as small as possible. Okay, and the second, and to make the critical path shorter, what you need to do? You need to simply make the critical input very close to the output. Okay, so if it is the case, in that case, you will get the better performance in terms of the propagation. So is the point is clear, or any doubt?
Yes, sir, it is clear.
Fine. So this is all about the input reordering. Next alternative solution could be like the logical restructuring. Okay, so what is this logic restructuring is? Suppose I have a function something like this: f is equal to a b c d e f g h. Okay, so what we can do, simply just what we are doing, simply we are ending all these things. Okay, so we are ending all these things. So the simple structure could be like this one. Okay, why I have made something like this? Can anyone tell me why I have used NAND and then inverter? See, I could have made like this one only, right? So all the inputs are something like this, and this one. This could be the simple one. But why I have used this structure? Can anyone explain? Or just guess? You can guess. It's not a like you just need to explain some things.
Sir, to get the inverted value, we can use not get, sir.
Inverted value, but why I'm just, so my simple question is, like, instead of NAND plus inverter, like this is nothing but this is the end of all these inputs, right? So this function is nothing but like this. So suppose I can keep like a b c d e f g h input, and then this is a simply AND gate, and here I can get the output. So this is also possible. So why I'm not using this block, but I am using this block?
So to speed up the circuit, to speed up the circuit, sir.
speed up the circuit, but the important thing is that another thing, how we will speed up the circuit?
Sir, TPLH in AND gate for is proportional to fan in factor, but in NAND it is not.
Okay. Anyone? Anything else? This is the simple. Like, see, the simple answer is, if I'm designing any circuit based on the CMOS, okay, so I can construct either NOR gate or NAND gate. I cannot directly construct the AND gate or OR gate. See, suppose I am keeping two transistors in the parallel here. Okay, this is the two transistors, and this is the two transistors here, and I'm making A and B, something like that. This is nothing but this is the NAND gate, two input NAND gate. Can you make the CMOS based AND gate? To make the CMOS based AND gate, you have to use one inverter just after this one. There is no, like, directly if you want to make the structure like based on the CMOS, you cannot make AND gate. Okay, you have to first make the NAND gate, then you have to invert it, then you can go for the AND one. And this is why I have kept like this. You got the reason, or any doubt?
Got it, sir.
Okay, so because see, in the CMOS based structure, we can just simply design the inverting kind of things. Like, we can design the NOR gate, we can design the NAND gate, we can design the inverter, but we cannot design OR gate or AND gate. So for that purpose, I need to use inverter just after the NAND one, and this is the reason why I have made the design like this. Okay, so so this is really very important. Like, suppose you are designing something, you're doing some research on that, and you have to design, let us assume, AND gate. So you have to first design the NAND, then you have to complement it, or you have to pass through an inverter, then you can get the AND gate. So this is the reason why it has been made. Now the thing is, we just understand in previous slide here, if we can go back to here, what we understand here is that, like, if I'm considering the NAND gate, so this TPHL is the function of the fan in. Okay, so if the TPHL is the function of fan in, what it means, if I have this much of input, like 8 inputs, in that case, might be for a particular technology, this NAND gate cannot sustain 8 inputs. So if I have the more number of inputs, in that case, delay will be higher. Okay, we just understand in the previous slides. Like, if I have more number of input in the NAND gate, the effective delay, or the TPHL, will be higher. And if effective TPHL will be higher, might be the overall delay will be higher. Okay, so the overall delay of this NAND gate will be very high, and then it will pass through an inverter. So to overcome this problem, what we can do, we can simply restructure this one. So suppose somehow I can use 2 NAND gate with 4 fan-ins. Okay, so this might be the delay, because this one and this one will work parallelly. Okay, so these two blocks will work parallelly, so the effective fan in or effective delay of this circuit will be same as this one, and then the total overall delay will be half. Okay, half than this one, and overall delay will be half than this one. Then it will pass through a NOR gate, then you can make it the same function whatever we have. Okay, so simply after restructuring the logic, you are what you are doing, you are simply reducing the number of fan-ins or number of input in a particular logics, and by reducing the number of fan-ins, you can reduce the delay or the overall propagation delay, and that will lead to the faster performances. Okay, so this is what the logic restructuring is. Similarly, we can do one more thing. Like, see here, but someone may ask, like, if the case is like this, I can use 2 fan in NAND gate, and then I need to make the NOR, then I can make the structure something like this one. Okay, so the structure could be like this as well, and this will give the same function. But what is the problem with this one? Can anyone tell me what is the problem with this one?
Sir, more number of gates, so I think the spacing between gates will increase, so area.
Area, yes. Any other? Okay, so let me explain. Suppose I am just restructuring this second logic with the last one. Like I am using the 2-input NAND gate, and then I have just made it the structure in such a way that the function will be same whatever we have at the input side. Okay, whatever with the first circuit. But the problem is, like, suppose this particular circuit will have some delay. Okay, and let us assume all this circuit has some delay. Let us assume T1 delay across all this one. Okay, so this NOR gate will act once it will receive the output from this one and this one. Okay, and this will also have some delay. Let us assume T2. So the output at this point I can receive after T1 plus T2 time. Okay, so T1 plus T2 time I will receive the output at this one. Similarly, at this point, if I am assuming the delay for this one is also the same, like the output at this point I will receive at T1 plus T2 time. Okay, and let us assume the delay of the and this AND gate is depends on the input of this one, this input and this input. So let us assume this is the T3. So this output is depending on T1 plus T2 plus T3, and similarly this depends on T1, T2, T3 and T4. So the total output will be received at T1 plus T2 plus T3 plus T4. So this is the total time that will take this circle will take to get the output. So if the internal delay, so what is the importance of this logical restructuring? The importance of this logical restructuring is to reduce the internal delay of this circuit. Okay, so the TPHL and the TPLH are the internal delay of any circuit. So by doing this, I am just reducing the internal delay. Okay, but if I am increasing more number of stages, that may lead to the overall delay or propagation delay between the inputs and the outputs. Okay, so this is also possible, but you have to optimize in such a way that the internal delay should dominate the external delay or the component delay. So this is very important. If the gate delay is started dominating the internal delay, then this is not the effective design. Okay, you got the thing what I'm saying? Or let me I need to repeat it again. This is really very important to understand. Do anyone have the doubt on this, what I'm saying? Simple thing is this.
Sir, can you repeat again?
Yes. So why I'm doing this restructuring? I am doing this restructuring to simply because I have used this NAND gate, and for NAND gate what I need to do, I need to reduce the TPHL. Okay, so the TPHL I have to reduce the TPHL. Okay, but the thing is I am just restructuring, logical restructuring, just to reduce this TPHL because TPLH will be same. Okay, so I have to do like this one, and if I keep on restructuring, so might be this T1 will be less than this T1. Let us assume TX. Let us assume the delay of this one is TX and delay of this one is the T1. So the T1 is less than T of X. This is perfectly fine. But the problem is might be I need more number of stages. Here I need 2 stages. One stage is this one and the second stage is this one. So let us assume the gate delay is TX for this stage. Gate delay is TX for this stage, and let us assume Ty for this one. So the total delay will be Tx plus Ty for the second circuit. But if you see the fourth one, T1 plus T2 plus T3 plus T4 will be the total delay. Okay, and if let us assume T dash, if T dash is less than T, then the second design is not good. But in other case, like if T is less than T dash, then this is the good, second design is good. So I need to consider the internal delay as well as the gate delay. So these T1, T2, T3, T4, Tx and Ty are the gate delay, and the TPHL and TPLS are the internal delay. Okay, so if I am reducing the fan in, then I am just optimizing the internal delays, and the overall delay will be reflected by all the individual blocks, how many we have connected, how many gates we have connected in the cascading. Okay, so this is really very important to optimize. So the point of consideration here is like, it is not important that like if I am doing the restructuring, so we need to extend the design in such a way that I need to use a 2-input NAND gate. Might be the third structure, whatever I just told you, this could not be the effective one, because this gate delay will start dominating the internal delays. Okay, so you cannot optimize the propagation delay. So you have to find an optimum way on which you can design your circuit in such a way that you will get. Yeah, so this is really very important. I think you have the cadence tool access. Just design this circuit, both the circuits, and try to find what is the delay in both the circuits, and that you will really be surprised like what are the factors which decides the delay, and that you will get to know about the real VLSI design. Okay, so this is important thing. That the point is clear, or still I need to explain?
No, sir, it is clear now.
Okay, fine. One more thing I just need to let me clear this one. I will write something here later on after taking the lecture, but for now I'm just clearing it. Suppose I have this kind of a structure. Okay, so if I have this kind of a structure, then what could be the other alternative? So suppose suppose I have the structure something like this, but I can design this circuit by this one. Okay, by this one, like I need to add 2 inverters, like this 2 inverter will act as a buffer. Okay, so what is the use of these 2 things? So after inserting the buffer in the circuit, okay, it will isolate the fan in from the fan out. Okay, so fan in and fan out will be isolated after using this one. Okay, so to improve or to even though, because the single unit inverter will have the less delay, so after inserting the buffer, the loading effect, whatever I was saying, like self-loading effect, that can be overcome. Okay, so this could be another alternative, like to so basically why we are using this one, this buffer is not affecting the functionality of this circuit whatever I have, but after inserting this buffer, this is going to isolate the fan in and fan out. Okay, and basically when this kind of circuit is used, whenever you have designed some circuit and you want to test on the test bench, on that test bench you have to insert the buffer in the fan in and in the fan outside, so that the self-loading effect can be avoided, and the self-loading effect will be avoided, then you will get the better performances. So always, like in a simulation setup, like if you are simulating some circuit, in that case you have to add some buffer before the circuit and the after circuit. Definitely this buffer is going to affect the functionality, but definitely the self-loading effect can be overcome, like this loading effect can be overcome. So this is the importance of buffer insertion in the circuit. So this is all about the different possible solution, how you can optimize the delay with the fan in, different fan in. Okay, so thank you so much. So that's it from the
sir, one question.
Yeah,
sir, one question from my side, sir. Sir, can buffer speed the circuit, or it can reduce the delay buffer?
See, the important thing is the buffer is having some delay. Like, see, I have inserted 2 inverters, so definitely they will have individual delay of both the inverters. Okay, but whatever the delay of this buffer is, might be it can reduce the loading effect in a such a way that the overall speed will be better. Okay, so if in this circuit might be there could be some self-loading effect. Okay, so if there is some self-loading effect, the overall like the delay of this will be something like, let us assume TD. After inserting buffer, this buffer, let us assume this is like T1. Okay, the total delay of this buffer is T1, and the delay of this one is, let us assume TD dash. Okay, and this, if I am talking about this TD is nothing but this TD plus self-loading delay, TD with the self-loading, TD dash with the self-loading. So this TD is nothing but TD dash plus TD self-loading. And if this TD self-loading is greater than this T1, then this design is poor. So this, but our objective is should be something like their delay of this buffer should be less than the self-loading delay due to the self-loading. And if we can achieve something like that, then the overall delay will be reduced. Okay. So that's it from the today's session. Tomorrow we will start a new topic, that is the different logic styles.